Okay, so we have to draw the picture that we were given, and in this problem we were given this picture. I'm going to change some of the variables that they provide to use the variables that I use in my lectures. So we have an inclined plane. That incline is at an angle of theta. So we don't know what that is. We just know it's some angle theta. Okay? So we can take that as being a general given. We have a box. That box is going down the incline. So it has some acceleration that's taking it down in that direction. We also have some forces that they identified acting on this box for us. We have this force, and they drew this, that's acting straight up. What's that force called? That acts perpendicular. What? Normal force. And what kind of force is the normal force? Is it a field force or a contact force?
Field, contact.
Contact force. You don't have the normal force if you're not sitting on top of something, if you're not on the surface. And this thing's sliding down the incline. And in this problem, we actually have friction. So friction exists now. What direction does friction go? Opposite to the direction of motion. Okay. This box is going down the incline, so what direction does friction go? Up the incline. Okay. This is good. You're all helping me solve this problem, so I won't make any mistakes, and it will be valid for the exam. So we'll call this force of friction. What kind of friction is this? Kinetic or static?
Kinetic.
Kinetic. Why? Because it's moving. Great. All right. Any other forces acting here? Gravity. What kind of force is gravity? It acts straight down, and is that a contact force or a field force? Field force. Gravity pulls you down no matter what. If I drop the scissors, what happens to them? They fall because gravity pulls them down. And now I step on that and cut my toes, and we all get out of class early. My shoes are falling apart, so they probably would cut straight through. Okay, so this is gravity. Let's label this gravity. This is all ungiven. I have to take this stuff, and I have to prove that equation for acceleration. Okay, any guesses?
Summation of forces.
Sum of the forces? Okay. Can I do them all in the same, just one equation to come up with the entire sum of forces? What do I have to do? I have to separate them, to do it in x and y directions. And what do I want to do with my x and y directions? Do I want things going left to be x and things going straight up to be y?
No, rotate.
What do I want to do?
Rotate it.
I want to rotate my coordinate system, so I'm going to rotate this coordinate system going down the incline. So here's my coordinate system. We'll draw that in. So that anything that's going perpendicular to the incline is the y direction. Anything that's going parallel along the incline is going in the x direction. If I'm going down the incline, do I want that to be positive or negative? That's kind of going towards the right.
Positive.
I like red things going positive. So we'll say going to the right is positive x, going to the left is negative x. Going up perpendicular to the incline is positive y, going down is negative y. Okay, so we set up our coordinate system. Let's shrink our picture down a little bit, and let's move it off into the corner. And what we're going to do is write the forces for the x and y directions. X direction and y direction. I always start in the x direction with saying what forces are going or acting in the positive x direction. Do we have any forces acting in the positive x direction? I see some. So acceleration overall is in the positive x direction. Well, what forces are causing that acceleration? FGX. Oh, I don't see that on here. I have to draw that in, don't I? So what I have to do is I have to break this FG into the x and y components. So to do that, I take the normal force, and the FGY portion of the normal force is acting directly opposite, and it goes straight down to this point right here. So that's FGY. And then FGX is going to be acting parallel to the incline. This is very important when you're doing these problems to draw these pictures correctly. So you always want your FGY force to be directly anti-parallel to the normal force, pointing the exact opposite direction. And your FGX, you got to make sure that that FGX is along the slope. It's parallel to the slope. You don't want your FGX to be a horizontal line. Gotta be parallel. So there's our triangle. And which one of these angles is theta? Is this one where the y and x? That's not theta. What's that angle?
90 degrees.
That's a right angle. That's 90 degrees. What's that angle?
Theta.
Theta. That angle.
Theta
90
2.0.
minus theta. Okay. So there's our theta way up there, up top. So we can label our theta. Great. We're making progress, believe it or not. So why don't I write my FGX and my FGY in terms of FG? Because I know what FG is. What is FG?
MG.
MG. Somebody chanted it in their sleep. Do it. I guarantee you. Put it on the exam. Maybe I'll make just that question the exam. Either 0 or 100. To know people would still get zeros. Make me sad. Okay, so FGX and FGY. What is FGX in terms of FG and the angle? Do we need to see that? Let's work that out. So let's take this triangle and work it out from scratch. I can write all the trig functions for this triangle.
Cosine?
So if I have, let's see, let's solve it out. Sine of theta
Yeah.
in this triangle. Sine is opposite side over hypotenuse. What's the opposite side in that triangle? FGX. So that's FGX over the hypotenuse. What's the hypotenuse? FG. So I want to multiply that FG over. I have FG times sine of theta equals FGX. So M times G times sine of theta is equal to FGX. Great. And let's write out the cosine of this. Cosine of theta. It's the adjacent side. What's the adjacent side? FGY. Good. Over FG. Multiply my FG to the other side. FG times cosine theta. This is the exact same stuff I just did last lecture. Exact same. M times G times cosine theta equals FGY. Okay, now we can finally write down the sum of forces in the x and y directions. What forces are going down? You said it earlier, FGX. Any other forces that are pulling this thing down the incline? Acceleration is where it's going. Acceleration isn't a force. That's the direction of the movement. So that's equal to mass times acceleration.
You said going down is positive.
Going down is positive.
Okay, so then minus friction.
Minus force of friction? Sure. Let's do minus force of friction. And that's equal to the mass times the acceleration. Do I have acceleration along the incline in the x direction?
Yes.
Yeah, they told us it was A. That's what we're finding. Hopefully. Fingers crossed. Okay. FGX. What is FGX going to be? Mg sine theta. Okay, so we're just going to plug that in. M times G times sine of theta. Minus the force of friction in simple friction. What is the force of friction equation if your friction is simple?
Normal force times coefficient of friction.
Mu, the normal mu, the coefficient of friction times the normal force. So that's going to be mu, and which mu is this? Mu k times the normal force equals ma. Absolutely. So the force of friction, when you're working in simple friction problems, is mu times the normal force. Mu is the coefficient of friction. Fn is the size of the normal force. Mu is something you look up in a book, usually. It depends on the surfaces that you have. So if I'm sliding, let's say I'm sliding a block of ice along this. Is that a big or a little friction? It's very low friction, right? Ice, very slick. If this is a sandpaper block, big friction. Okay? So that friction, that number mu, becomes closer and closer to 1 as your friction increases. So we have this. We're looking for, what are we looking for again? Acceleration. Keep that in mind. We need to find acceleration. So let's divide both sides by m. And now I've got this big giant equation, Cancel out my m's. I'm going to get A is equal to m times g times sine of theta minus mu times the normal force divided by m. Does that A look like this A?
Not quite.
I see some things. Right? I got a G here, and I got some G's over in that equation. That's good. I got a G there. I have a sine of theta. That's good. And I have a sine of theta there. I have a mu, and I have a mu. Ah, shoot, but I got Fn. What do I do with the Fn force? That's the job. What do I do with the Fn force? How do I find Fn?
Put it in terms of maybe the y direction.
Maybe let's look at the y direction, see what's going on in that direction. So let's take the y direction and do the exact same thing that we just did. What forces are acting up? Fn, the normal force. So the normal force you can see is acting in that positive y direction perpendicular to the incline. Anything else acting up perpendicular to the incline? See any other action? I don't see anything. Okay, anything acting down? FGY? So what do I need to do with FGY? I subtract my FGY. Minus FGY. And what is that equal to? Am I bouncing up and down as I'm going along this incline? Is there any acceleration perpendicular to the incline? So what's the mass times acceleration in the y direction? Zero. So this is equal to 0. These equations, these sum of force equations, where do I even get those from?
Your brain.
My brain. And why does my brain know to do that? Who can I credit with this?
Isaac Newton.
Newton. Which law? Newton's second law. Sum of forces equals mass times acceleration. So that's what I'm writing down every single time I'm doing this. This is Newton's law for this problem. This is Newton's law for the y direction for this problem. So let's see what Fn is. Fn minus FGY. And what was FGY? mg cosine theta equals 0. So Fn is equal to m times g times cosine theta. Fn minus mg cosine theta equals 0, so I add mg cosine theta to both sides, and that moves it over. You know, I ask you so many questions, and it seems like I forget these things all the time. I'm concerned that people on YouTube are going to report me as being like senile or something, losing my memory. Seems like I never know what I'm doing. What do we do with this Fn then? Let's plug it in. Let's plug in for Fn and see what happens. So I have m times g times sine of theta minus mu times the normal force. What's the normal force?
Mg cosine theta.
M times g times cosine theta. And then I divide all of that by m, and that's equal to a. What happens to m? I have an m in every single term of this, so the m's all cancel each other out. So I can divide the m out of all of these, because there's an m in every single one. So now I have g times sine of theta minus mu times g times cosine theta. That equals a. What can I do with the g? I can factor that out, so I factor out a g, and then I can distribute that into the sine theta minus the mu times cosine theta, and that equals a. And what do we do with final answers? Circle final answers. Question for Brooks? Oh, it's still there. I'm too fast and loose with the mu k's. Okay. So that's what we just solved. A equals g times quantity sine theta minus mu cosine theta. We were looking for A equals g times sine theta minus mu times cosine theta. Can I test you on chapter 6?
Unfortunately.
Yay! Woohoo! Wish I could toss in a party much. Questions? Nah. Let's do chapter 6. So we just did math with just letters, no numbers. No calculator needed.
Do you think this is the information that we can use for
So this you could use for any block that you have sliding down an incline that has friction to find the acceleration. Work for every time. Does it matter what the mass of the block is? No. That seems crazy. The acceleration of a block going down the incline is the same no matter what, it doesn't depend on the mass. It's crazy. So if I take a giant block of ice and slide it down an incline, it's going to go just as fast as a block of ice that you just get out of your refrigerator. Why? Yes? Uh-huh. Μk is the coefficient of kinetic friction. It tells you how much kind of stickiness or roughness there is between two surfaces. So if I have a block of ice that I stick on something, there's a very low mu because the block of ice will slide really easily. If I have a sandpaper, that won't slide very easily, so that has a high friction. It depends on the surfaces that you're talking about, and that's a number you go and look up in a book. There's tables of it. Engineers have figured these all out for you. All right, go ahead. Any other questions on this one? Your in-class problem is very similar to this. You will derive a very similar equation. Except I think it's for if you don't have friction. Any other questions? Okay, go for it. Solve problem 52.